So good morning, everybody. I sent a message on the chat box. Please, can you reply the message so that I will know how to go about today's lecture? You're busy writing your names and the matric number, which is okay. But please, can you address my question? I asked a question on the group chat. If not, I'm going to do it my own way. And that is almost now. I have 4 minutes to start the class. I don't know what is yes, ma. Because I have all there. Okay, we are going to do a recap. In as much as I'm not seeing you, I believe in you. And I believe you will do all I ask you to do to make this seamless and, we can be fast about it because I have to round up my lecture with you today. Now, can you please have a biro and a paper beside you? What I mean is your writing material, your notes for Fsc112 and a biro to write with. Please get them beside you because I think if you do more of the writing down, it's going to help us better. Thank you so much. We have 3 minutes, so get your writing materials ready. You have 2 minutes to start the class. Get your writing materials ready so that when we start, it's going to be seamless. Not only that, and we are going to be fast about whatever we are doing. I'm just holding on for the time so that it will be that I started before the time, and some people have not logged in. I'm equally talking to those that are being that are using YouTube, those that are listening live on the lecture. Please get your writing materials beside you. Please, it's going to help us. All this recap on quantum numbers and all of that, if you don't write these things down, you really cannot get it fast. I know what I'm saying. When I say put N, when you put it, you look at it, you know what L is and what L is. That's going to make it faster for us. So it's time we have to start the class. So once again, I welcome you all to today's class. We're going to have a recap on the quantum numbers again, but this time around, we're going to be faster. Now, let's start with the 4 quantum numbers that describes an electron. Like I said, we have 3 quantum numbers that will describe an orbital and 4 quantum numbers that will describe an electron. So we're going to take all of the 4. Now, the first is the principal quantum number. The principal quantum number is designated as small letter n, and this is small letter n here. And the function of this quantum number is to determine the energy of the orbital that you're discussing and the distance of the orbital from the nucleus. Now, The smaller the value of N, the lower the energy. That's, you know, I know it's just how to use it to describe orbitals and electrons that you care about. Now let's go to the second one. Oh, sorry. The second one is the angular momentum quantum number, or what you call your azimuthal quantum number. Now, this is what gives the shape of the orbital. When we talk about the shape of the orbital, remember that when I described the types of orbital for you, we looked at S, P, D, and F orbitals, and each of these orbitals has its own shape. Remember, you saw the shape of the S orbital, which we said is spherical. You saw the shape of the P orbital and the D orbital, the dumbbell-shaped orbitals. And we said that for the F orbital, that the shape is complex, and all we should know is the number of orbitals that is comprised in this, the number of orbitals that we have in this subshell. Now, for the angular momentum quantum number, is designated, or the notation is italicized small letter L. And this quantum number has values from 0, 1, 2 to n minus 1. So the maximum value of L is n minus 1. So we've defined n previously. And I told you that means that L, which is the angular momentum quantum number, is dependent on the value of n. Now, for a given n, there will be n different values of L. What does this mean? If you have the energy level, that is the principal quantum number, which is describing the energy level of an orbital or an orbital occupying an electron. If you have n equal to 1, L is going to be equal to 0. So it will have only 0 at its angular momentum quantum number. This is because for every n, you have values from 0 to n minus 1. And 1 minus 1 is 0. So you cannot have 0 and 0. You can only have 1 0 for a particular L. Am I communicating? Now, I want to go to the next slide for something. For each L value, there is a corresponding letter label that is associated with each L value. When L is 0, it signifies the S orbital. When L is 1, it shows that it's a P orbital. When L is 2, it shows that it's a D orbital. When L is 3, it shows that it's an F orbital. Please, can you put this down on your notes now? L equal to 0, S orbital. L equal to 1, P orbital. L equal to 2, D orbital. L equal to 3, F orbital. We can stop at F for now. Now let's go back again to the previous slide. If we say that n is equal to 1, that means that 1 minus 1 is 0. L is going to be 0, which means that this particular, any electron that you found in this energy level for this particular orbital is going to be 1s, because 0, for L equal to 0, the label is s orbital. So this is going to be 1s. So the electrons here will be accommodated in the s orbital and the energy level 1. Now for n equal to 2, n equal to 2 is going to be n minus 1 is 2 minus 1 is 1. But remember that the value of L starts from 0, 1, 2, 3. And before you go to 1, you must count 0, isn't it? So if we say that 2 minus 1 is 0, that means that for n equal to 2, L is going to be 0 and 1, because 1 is going to be the maximum value, but it's going to start from 0. So you cannot just say that n is equal to 2, that L is only 1. Am I communicating? L is going to be 0 and 1. And remember that means that for this n is equal to 2, electrons that are found here are found in 2s and 2p orbitals, because L, for L equal to 2, the symbol is s, And for L equal to 1, the symbol is P. So you have 2s and 2p. So electrons will be in 2s and 2p. Now let's go to N equal to 3. For N equal to 3, you have L equal to 0, 1, 2. How did you come about the 0, 1, 2? 3 minus 1 is 2. But remember, the value of L starts from 0. So before you get to 2, you must have 0, 1, and 2. So for L is equals to 3, you have 0, 1, and 2. This means that electrons found here are occupied in the 3s orbital, 3p orbital, and 3d orbital. These are the possible orbitals that this electron can go into. Now, for N equal to 4, N is equals to 0, 1, 2, 3, 4. Yes, because N is 4, 4 minus 1 is 3. But you have values from L starting from 0. So before you get to 4, it's going to be, before you get to 3, it's going to be 0, 1, 2, 3. So if you have an atomic orbitals with electrons here, it's going to have electrons in these orbitals, 4s, 4p, 4d, and 4f. That is where you have orbitals. Now, the last example I had with you in class is such that you have electrons in the 3s and the 3p. The 3d is here, but because there are no electrons there, if I ask you what is the L quantum number for sulfur, it's going to be N equal to 3, N equal to 0 and 1, because the electrons for sulfur are accommodated in the 3s and 3 orbitals only. There is no electron in the d orbital, so you don't need to write these 2. This 2 is available. Maybe there could be excitation of electrons from p orbital to d orbital. But at that ground state, or at the state that the question was given, there is no electron in the d orbital. So this is not going to be, you're not going to use 2, L equal to 2, to describe the electron for sulfur atom. Having said that, we go to the third quantum number, the magnetic quantum number. The magnetic quantum number, I told you that the L is the magnetic quantum number, ML. There's a subscript L here, please. Is dependent on L value. And it has values from minus L to 0 to plus L. So you don't need to worry what you have. All you need to do is, once you have the value of L, if the value of L is minus 1, you're going to say that your ML is minus 1, 0, and plus 1. If the value of L is minus 2, your ML is going to be minus 2, minus 1, 0, plus 1, plus 2. It's as simple as that. Now, for a given L value, there will be 2 L plus 1 values of ML. Let us look at what this means. What this means is that if I have L equal to 1, that means that I have 2 times 1 plus 1. 2 times 1 plus 1 is equals to 3, isn't it? Let's look at if this is correct for ML. We said that ML is minus L through 0 to plus L. So if L is equals to 1, therefore ML is equals to what? Minus 1, 0, plus 1. These values, are there 3? Yes, they are 3 because minus 1 is 1, 0 is 2, plus 1 is 1. That is 3. Now, if I say that L is equals to 2, L is equals to 2, that means that my ML, which is the number of orbitals that I have, is going to be 2 times 2 plus 1. 2 times 2 is 4. 4 plus 1 is equals to 5. Let's see if this agrees with what we have from looking at minus L to 0 to plus L. Now it's going to be minus 2, minus 1, 0, plus 1, plus 2. Now these values, are they up to 5? Yes, they are 5. Minus 2 is 1, minus 1 is 2, 0 is 3, plus 1 is 4, plus 2 is 5. So whichever way you want to, whichever method is easier for you, whichever formula is easier for you, please use it. That's why I'm bringing in different things. If you think that you can go with 2L plus 1, that is fine. But you can see that we are still getting the same thing when we are using minus L to 0 to plus L. Now, for this particular slide, what I did here is to bring out what we mean by saying that ml value is minus 1, 0, and plus 1 for L equal to 2. I mean L equal to 1. These are the values of your L. If L is 0, the number of orbitals you have is going to be 1 because your ml is 1. And that is if L is 0, you just have s orbital. So it's just 1 orbital. 1s is 1, 2s is 1, 3s is 1, 4s is 1 orbital. So there's nothing like 2 orbitals. Now, if L is equal to 1, the label is p, isn't it? Is a p orbital. And we know that p orbital has 3 degenerate orbitals. And so the number of orbitals is going to be 3. And that 3 is going to be what? 2px, 2py, and 2pz. That is why you have minus 1, 0, plus 1, because your ml shows the direction of these orbitals. It gives you the direction of this orbital. Now, this one is pointing towards xy. This one, that is why you have 2px, 2py, and 2pz. Now, if your L is equals to 2, that shows that it is the d orbital, isn't it? That the d subshell, I mean. And you have 5 degenerate d orbitals. Now, those degenerate d orbitals, you know their directions are different. You have dxy, you have dxz, you have dyz. Sorry. Then you have dx squared minus y squared. Then you have dz squared. The ml is just telling you the direction of your orbital. For s is just 1, it's spherical. That is why you just have 1 s orbital, and it's showing here in the number of orbitals. So I think I am being explained. Look at one class, and once you get this right, I will be fine and I will be relaxed. So I have a question here. Okay, let's go to this. I think you need this also. Now, what's happening? Like we said, 3 quantum numbers will define an orbital, and 4 quantum numbers will define an electron in an orbital. So for this particular orbit, we want to look at what we have said previously. If n equal to 1, n is 0, ml is 0, you have 1s. If n equal to 2, L is 0 and 1, isn't it? If n is equal to 2. So you're going to take them 1 at a time. Let's take L is equal to 0 for n equal to 2. That means ml is equal to 0. You have your 2s. Now remember that n equal to 2, you also have L equal to 1. So ml is going to be minus 1, 0, plus 1. And these are your 2px, 2py, and 2pz. Let me see on the chart if you understand this very well. Please write down on the chart. Well understood. Can I see that? Can I see that, please? Well understood. On the chat box, well understood. On the chat box, good. Well understood. On the chat box, on the chat box, on the chat box, well understood. On the chat box, I'm still seeing some people that are saying I don't understand. So me, I don't know how to explain it again. You can meet me personally. Yes, well understood. Can I see more of that? 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 Please don't ask me stupid questions here. Don't ask me where you can meet me personally. I have an office. I don't want to be rude to you, so don't be rude to me, please. Yes, well understood. Good. So I'm seeing more of well understood. Now, can we go to the next slide and see if we can handle this question then we are good to go. Now we have here, what are the possible values of L and Ml for N equal to 1 and N equal to 2? What are the possible values of L and Ml for N equal to 1? That is, hydrogen in the ground state is N equal to 1. Hydrogen in the excited state is N equal to 2. That is why we said N equal to 1 and N equal to 2. So can we go on? What are the possible values of L and Ml for H in the ground state and its excited state from N equal to 1 to N equal to 2? So let's start with N equal to 1. N equal to 1, what is L? Let's go to the chart. For N equal to 1, what is L? Good. L is 0, good. Good. What is Ml? What is Ml? Good. N equal to 1, L equal to 0, Ml equal to 0. Good. Now, can you please write the electronic configuration? Write it out. Is it 1p? Is it 0p? Just that way for N equal to 1. Can you give me the good 1s exactly? Good, correct. 1s, correct. 1s, correct. Good, 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 good. I'm happy. Now let's go to N equal to 2 quickly. We still have periodic table to deal with. Let's go to N equal to 2. N equal to 2. N equal to 2. L is going to be what? Please differentiate the two values of L for N equal to 2. L equal to 2, L is going to be what? And Ml is going to be what in each case? So let's go to the chart again. Those of you that are on the YouTube, please, I hope you guys are writing down something. Good. For N equal to 2, L equal to 0 and 1. Yes, I want to see it that way. Correct. Please give me all the values of L for N equal to 2. And give me all the values of Ml for each of the L. Separate them. For L equal to 2, you have 0 and 1. Then L0, Ml is what? L1, Ml is what? That's the way I want it. So Bimbo, you go back to rewrite your own. Exactly, 0 and 1. You just gave me Ml equal to 1. I need L equal to 0. What is Ml? I need L is equal to 0. What is Ml? It's only one person that's giving me what I want. N equal to 0. Yes, you have two values of L, which is 0 and 1. Now, for 0 and 1, give us their Ml values. Exactly, that is what I want. I didn't say you should tell me the degenerate orbitals. Ml is -1, 0 and 1. For which L? For which L? Is 0 and 1, I know. Good. When L is 0, M is 0. When L is 1, Ml is -1, 0 and +1. That is how I want you to put it. Take them one by one. Yes, when L is 1, Ml is -1, 0 and +1. When L is 0, what is Ml? Exactly. Osasai, I can see you. I want them spelled out. Good. Who is Zoom user? Bimbo iPhone. I can see. Good. Exactly. This is what I want. N equal to 2. L is 0 and 1. Ml for 0 is 0. Ml for 1 is -1, 0 and +1. Now I'm going to ask you a question now. That is the reason why I say you should just split them out. Now for N equal to 0, what is the total number of orbitals for N equal to 0? what is total number of orbitals for n equal to, for n equal to 2? What is total number of orbitals? Sorry, for n equal to 2. For n equal to 2, what is the total number of orbitals that n equal to 2 will have? Total number of orbitals. Remember, you're looking at your ml, both 0 and no, is not 5. No. For n equal to 2, exactly, somebody got it. For n equal to 2, what is the total number of orbitals? It's not 3. That's why I say you do for 0 and you do for what? For 1. It's not 3. It's not 3. It's not 3. It's not 1. It's not 2. For n is equals to 2, what is the total number of orbitals? It's not 9. Let's go to the next slide so we'll see the answer and we'll go to. I just saw what's happening. Okay. Now let's look at what we have. Let's look at what we have. For n equal to 2, forget about n equal to 1. We are not using n equal to 1. For n equal to 2, our L is 0 and 1, isn't it? Now we are going to take this L, that is the angular momentum quantum number. We are going to describe them for this electron one by one. Now I'm taking L equal to 0. ML is going to be 0. Then I will take L equal to 1. ML is going to be -1, 0, and +1. So you know that it is the ML that tells the total number of orbitals that you have. So here you have what? 2s, 2px, 2py, 2pz. So you have how many orbitals in all? 4 orbitals. The 2s orbital, the 2px orbital, the 2py orbital, and the 2pz orbital for n equal to 2. Because n is equal to 2, you have 2s and 2p. Are we together now? For n equal to 2, you have 2s and 2p. So s actually is still an orbital. So you're not considering only the p orbital for n equal to 2. Because n equal to 2, you have 2s, which is ml equal to 0, and you have 2p, which is ml equal to -1, 0, and +1. So for n equal to 2, you have 4 orbitals comprising of 2s and 3 2p's, the p orbitals that are degenerate, making 4 orbitals. Now, can you please quickly tell me the number of orbitals that you have when n is equals to 3? The total number of orbitals when n is equals to 3. The total number of orbitals when n is equals to 3. The total number of orbitals when n is equals to 3. So let's go to the chart. We are done with n equal to 2. You can get that in your slide. Yes, a lot of you're getting the answer for n equal to 3. But my question is, do you understand how you got the 9? Just tell me yes, and we are good to go. For n equal to 3, good. They said exact. Thank you so much. Thank you so much. Almost everybody is getting n equal to 3. For n is equal to 3, what is the total number of orbitals that we have? Exactly, somebody now had to do what? To describe it very well. The S, the P, and the G. Exactly, you guys are making me happy. For n equal to 3, how many number of orbitals? Total number of orbitals for n equal to 3. Exactly, for n equal to 3, the total number of orbitals, 1 plus 3 plus 5. That is correct. Great. You guys are making me happy. Exactly. For n equal to 3, you have 0, 1, 2. Good. Then the 0, 1, 2, how many orbitals are in each of them? Because the question I asked is number of orbitals. Now you got the type of orbitals or the levels, if that's how you want to say it. But what exactly? The total number. Exactly. 1 plus 3 plus 5. Now, can we move on to what we have for today? Because this is just a recap, it's not today's. Exactly, it is 9. Thank you so much. For those of you that don't understand it, please try and see me. I'm going to give you a time on a Monday so that I will be able to see many of you at a time. It will not be nice seeing you 1, 1, 1, 1. The stress will be too much on me. So let's see on Monday. I don't know how your timetable is, but if we can move it on Monday, let's say between 2 and 4, is it okay by you? Yes, it's going to be a physical meeting, but I know your names, though. I've been putting down, if you, those of you online, you see that I have a note beside me. So if your name is not here that I've written down, don't come and disturb me. Those of you, all these people that are doing well, Bimbo them, what's these other names? I have a lot of names here. Don't come and disturb me. As a matter of fact, you should be the one teaching your classmates. But let me just say that, let me teach them for now. Some on YouTube, I know, and that is why I'm saying some of you that are seeing me online. You could see that I have a note, so I'm putting down names of people. So you don't just come and, not that you're disturbing me anyway, but since you understood it, why don't you allow people that don't understand it to see me? Akinde Ezekiel, you understood it, so I don't want to see. If I see you near my office, I'll give you a knock. So let's go to today's class. Want to look at, the class is going to be brief anyway. Brief periodic classification of elements and its relationship to their electronic configuration. Thank God we've done electronic configuration. And remember I told you the core electrons and the valence electrons. And I remember that I told you that it is the valence electron that actually determines or confines the chemical properties to a particular element or atom. And I told you that this has to do with the bonding ability or the magnetic property of that particular atom. And we went on to look at the paramagnetic and the diamagnetic property of an atom. And we said that for paramagnetic is when the atom has an unpaired electron in the orbital, it is paramagnetic and they're attracted to a magnet. Diamagnetic, when it's that, it's all the electrons are paired, these are not attracted to a magnet. Now I want to look at how do we classify these elements in the periodic table. Now, I don't want to bog us into the history of periodic table. That will meet when we are doing, I think, CHM 211. But all I want us to know is that we have periodic table classified in the S, P, and G, and F blocks. But for now, we are going to concentrate on the S and P block. You still have the G block and the F block. We're going to see them, but our concentration will be on the S block and the P block. Now, when we talk about periodic table, we say that it's a tabular arrangement of elements in the order of increasing atomic number. Remember, what defines the atomic number is the number of protons that actually signifies or tells you the atomic number of an element. So this is being used to actually arrange them in form of a table. And so this is the table. This is the periodic table. Now you have the columns. The elements are arranged in groups based on columns. In their columns, you have group 1, you have group 2, you have group 3, you have group 4, you have group 5, group 6, group 7, and group 0. Now, if we are considering the transition method, in some textbooks, the group 3 will become group 13, group 14, group 15, group 16, group 17. It's just taking care of these 10 groups within the transition method. Now, you also have the horizontal parts of the periodic table, which are represented as the periods. Now you have the period 1. In the period 1, you can see that there is helium here. You have your period 2. Period 2 has lithium through neon. You have your period 3, period 4, and so on and so forth. So the periodic table is being arranged in groups in columns, and the elements are also arranged horizontally in their periods. Now, like I said, each element are arranged in the order of their atomic number, and the elements in each group, they have similar properties. Now, the reason the elements in each group have similar property is because in each group, they have the same valence electron. For group 1, their valence electron is 1. The valence electron is the outermost electron. For group 2, the valence electron is 2. For group 3, it is 3, and so on and so forth. So because they have the same valence electron, and I remembered in our class on Wednesday, I told you that it is valence electron that actually confines some properties to these elements. So elements in each group tend to have similar properties. Now, across a period, they change in their properties. This is because across a period, elements do not have the same number of valence electrons. What they have is the same number of shell. So you keep on adding electrons to the same shell across a period. Now we've known this, let us take some examples. Now, this is elements in group 1. These are group 1 elements. This is what I am saying. For the group 1 element, why did I jump to group 2? For group 1 elements, look at their valence electrons. They have electrons in different shells, but the electrons are the valence electrons are the same. 1, 1 on each of the orbital. This is 2s, second energy level. This is 3s for sodium, third energy level, but they have their valence electron accommodated in the s orbital, and each of them has 1 electron each. So based on this, they will exhibit similar properties. Now again, let's look at elements in a period. Sorry. Now, I told you that in the horizontal row, you have them classified as elements in the period. Now, these elements, they differ in their property because for each element, there is an addition of electron to the electron shell and a proton to the nucleus. Reason being that electron is being added to the same shell. For lithium, electrons are found in the second energy level. You have the electron accommodated in the s orbital, 1 electron. As you go across the period, you get to beryllium. You have another electron added in the same orbital, which is your 2s. Now the s orbital is filled up, but you still have available p orbital in the second energy level. That is the 2 n is equal to 2. That is your 2p. Now when you get to boron, boron has 5 atomic number, and boron has 7. The atomic number is 7. No, I mean 5. Sorry about that. It is 5. It's actually looking out on me. Boron has 5 atomic number, and the valence electron is 3. Now, electrons are accommodated in a different orbital, which is the p orbital. So these are the things that make their properties not to be the same. So they have different properties because they do not have the same number of number of valence electrons. Again, carbon with atomic number 6 has electrons, another additional electron in the p orbital. So it has 4 valence electrons. Boron has 3 valence electrons. Beryllium has 2 valence electrons, while lithium has 1 valence electron. Because of difference in their valence electrons, they exhibit different properties. When I talk about properties, I'm looking at the physical and their chemical properties. You could see that here, there's an additional electron as you go across the period. So this is actually showing us a summary of what we have said to look at the valence electron. Now for group 1 element, you could see that we have NS1. N can be 2, it can be 3, it can be 4. But what is the same here is the number of electrons and the orbital. So the electrons are accommodated in the s orbital, and each of the elements in group 1 has 1 electron. Hence, they will exhibit similar properties. The same for group 2 elements. For group 2 elements, the valence electron is in the s orbital and each has 2 electrons each. This goes down to group 3, where you have, okay, I have to remove this so you can see. Oh, sorry. So the group 3 elements where you have ns2, that is 2 electrons on the s orbital and 1 electron on the p orbital. For all the elements in this group, for all the elements in each group, they will exhibit this valence electron. Now, like we said, this also gets to affect their periodic properties, which includes the atomic radius, the ionic radius, the ionization energy, the electron affinity, and the electronegativity. I'm not going to go into details on this. I just want to show you that there's a gradual change in, there's a change in this, in the properties, in the periodic properties of these elements. Now again, in as much as we have the same valence electron as we move down the group, there tends to be a gradual changes in their certain physical properties. Reason being that as you go down the group, you have some kind of shielding effect and all of that. Because as you go down the group, you're adding shell. You're adding an extra shell to what you have. So electrons at the outermost shell, which are your valence electrons, as you move down, tends to be further away from the nucleus. And as such, they do not experience that attraction. Remember that in your nucleus, you have the proton and the neutron. The proton is positively charged. In your shell or the orbitals, you have the electrons. The electrons are negatively charged. So there is usually an attraction between the negatively charged electron and the positively charged proton in the nucleus. So they used to experience this slight attraction between them. Now, positive, negative will always attract because they are opposite signs. It is the same signs that does what? That repel each other. Now, because of this distance, there tends to be changes in their certain physical properties. Again, I said, we are not going to go into details on this. It's just for your knowledge. By the time you get to 211, I think it should be dealt with. So let's move on because we must finish this class today. Now let's look at the atomic size. The atomic size. Then the size of the atom decreases from left to right across the periodic table. So as we move from lithium, beryllium, boron, carbon, and so on and so forth, their size decreases. Like I said, this is because you are adding an extra electron to the same shell across a period. You're adding an electron to the same shell. And when you're adding an electron, you have one extra positive charge to the nucleus. So you have that. So that tends to do what? To decrease the size as you move down the period. Then while descending the group, the size increases. The size increases because you're actually taking the electrons further away from the nucleus. So the attraction will be what? It will be less. So they tend to grow bigger. But when they go across a period, as you're adding more of the electrons in the same shell, they tend to shrink, they tend to shrink or come closer. Example I will give you is this. If you have a class and you have a chair, maybe in your you have the first row, that first row will accommodate 5 people, but it's not by default. But I want it to accommodate 10 people. The only way that first row, which is meant for 5 people, can accommodate 10 people is if it becomes tighter, that each of you have to do what? Maybe you don't need to sit and balance well. It needs to close and come together so that extra 5 people will, because all I want is this row must take 10 people. I don't know how you want to do it, whether you want to cut off your size, but I want you to take 10. So what you will do is, you know that you start doing what? Even in the bus, when you enter a bus, that's supposed to take 3 people. Now this VRC campus, they're not taking 4. You could see that it's tight, you know, that is decrease in size. So as you go down the period, the size tends to do what? To decrease. Now, while descending the group, I'm going for, I'm not supposed to be saying all of this. While you go down the group, it's as if you're even bringing more seats. Shift, let me balance. You know, everybody will now have space, and you know, the size will tend to do what? To increase. That's all I can say as regards to atomic size. So let's move to the next one. We have to be fast. I must have to finish this class today. This is what we are saying. The atomic radius, like the atomic size, it increases down the group. Let's see what it does across a period. I'm going to give you the slide, please. I've explained it. So you can see that across the period, what is happening across the period? Across the period is decreasing. From sodium is decreasing to what? To chlorine. So that is all you need to know. Now, what happens to ionization energy? The definition of ionization energy is there for you. Wow. Sorry. So it is the energy required for an electron to remove an electron from an atom, and it reduces as the size of the atom increases. So what you will say is this. It is just an opposite of what? Of atomic radius. Ionization energy is opposite of atomic radius. So what this means is that when you get down the group, the ionization energy will do what? It will decrease. As you go across a period, the ionization energy will increase. So down the group, the first ionization energy decreases, then across a period, it increases. Now let's look at electron affinity. That is another property, it's a periodic property. It's a change in energy in kilojoule per mole when an electron is added to a neutral atom to form a negative gaseous ion. It is here you have an atom, an electron, then you have the negative ion. What happens to the energy? Now, there is something about the electron affinity when you go across a period. But let's start with down the group. Electron affinity will decrease down the group in a periodic table. This is because your N will increase. That is the size of as the size increases, the affinity for the electron will less. Remember, the affinity for the electron will be further away from the nucleus. So as you go down the group, the electron affinity decreases. Now, as you go across a period, the electron affinity will either decrease or increase, depending on the electronic configuration of that element. Remember that the elements will always want to be at a stable state. Now, some elements, they have what we call the half-field stability. For example, your nitrogen. Your nitrogen has the 3p orbital with single paired electrons. And so it prefers to remain in that particular format because it's more stable there with that unpaired electron at each of the p orbitals. So it will prefer to be in that format, and so carbon will have a greater affinity for an electron than nitrogen. Nitrogen does not need electron because the energy it will require is higher. You know, it prefers to be at that half-field stable state than taking an electron. So in that case, electron affinity fluctuates. So based on the electronic configuration. Like I said, you're still going to get more of this in your 200 level. I'll check the time and see what we have. Now, the last but not the least is electronegativity. Electronegativity, which is the ability of an atom to attract an electron towards itself. Now, it attracts an electron towards itself. If you have this, you have the electrons coming towards the partially negative element or atom. Now, For metals, they have low tendency to attract electrons and high tendency to release electrons. If you look at the metals that you have, let's say from, let's take for example, let's say group 1, group 3, yes, group 3 elements. Let's go back to the table of periodic table. Okay. Oh. Okay. Now you have your metals from group 3 here. You see that they have low tendency here to give out the electrons because the ease of attraction is better here. And this increases as you move down the group. If you look at your group 1 and your group, the non-metal, no, these are the metals. Those are the alkaline metals. Those are the alkaline metals that you have here, that you have the 1 electrons and the 2 electrons. For the 1 electrons and the 2 electrons, the ease at which they will give out their electrons is very, very easy. So they give out their electrons so easily. Now, these ones here that you have here, the electrons here are 3, so they will prefer to gain the electrons in order to be stable. For example, here you have fluorine, which just need 1 electron to be stable. So it's better for fluorine here to take 1 electron than to give out its 7 electrons in the outermost shell. So for the elements in this category, left, the metals at the left, it is easier for them to do what? To take electrons than to give out electrons. This is because the energy required to give out all of these electrons is much. So it prefers to take 1 electron and become stable and become 8 here. So also oxygen. Oxygen will prefer to gain 2 electrons than to lose these 6 than to lose these 6 out. So that is what we mean when we say that they have the low tendency to attract electrons. Now for the electronegativity, the trend is this. As as you move down the group, electronegativity, what? It decreases as you move down the group. It will decrease because remember that electronegativity is the ease that you give out your what? Electron. The ease that an electron is being given, the ability of an atom, the ability of an atom to attract electron towards itself is electronegativity. I'm mixing it up with the other electron affinity. The ability of an atom to attract electron towards itself. So as you move down the group, electronegativity will decrease. Now, electronegativity will increase moving across a period. It will increase moving across a period because as you go across a period, like I showed us in the second period, it will be easier for your lithium to give out its electron. When you move down to fluorine, it will not be easier for it to give out. It will be easier for it to attract. And electronegativity is what? Is attracting electron towards the atom. So as we move down the period, electronegativity increases. Now, this is a summary of the periodic table. So you see the color here, group 1 and group 2, you have the S block elements. From group 3 to group 0 here, that is 3, 4, 5, 6, 7, 0. You have the P block elements. Then the transition elements are between group 1, 2, and group, that is between the S and the P block. You have the G block elements. Again, between this D block, you have the F block. Now, The summary of the periodic trend or the periodic property is that down the group, atomic radius increases. Down the group, electronegativity decreases. Down the group, shielding effect increases. Down the group, ionization energy decreases. Across a period, atomic radius decreases. Across a period, electronegativity increases. Across a period, shielding effect is constant because across a period, you're adding electron to the same shell. Then across a period, ionization energy increases. So that is all we have. And please, if you have any question, I know that I rushed this last class because I need to finish the class today. But if you have any question, please, you can put it down. I don't know. When you see me, you can ask me the question. Let me just put it that way. Because putting it down, I'm no longer here. I won't be chatting with you again here. And but we still have like 9 minutes. So let's go to question and answer on our group chat and take some questions. Please, I want to take some questions. Can I take some questions? Don't be asking me where is your office. Ask me a question about today so that others can partake in the question. Can you please put down your question if you cannot? Put down your question on the group chat. Any question that we can answer within this short time? Hey, you have a question, ask the question now. No question, ma, it's not you. No question, don't say no question. Don't tell me no question. No. Okay, I'm putting down the questions. I want to get this clear. What's happening?
Hello, ma.
Hey, Dr. Strang.
Can you hear me?
I can hear you.
Can we tell them? I want to tell them that they should confirm with me the class reps. I want to make sure all the lists I have with me are the class reps for the various departments. Because
okay, so they should meet you.
Sorry?
You want them to meet you?
Yeah, they should. If they are not registered with me as class rep, they should because I want you, based on what you've done, based on what the three of us have done so far, we can decide some questions together.
Okay.
And they will do online tests.
Okay.
We can get across to all of them through their progress, because we are only going to copy, and they are going to do the test online. So we need to be able to get to the class so that they can copy the link that we're going to send to them to their class member.
Okay.
So that's why I want you to ask them now, so that.
Okay, sir. So, can you hear me? Talk to them directly. I think they are hearing you. Fine. And you can ask them. They can hear you.
That's the message I want to pass. Students, please inform all of our class members that have not registered with me to try to do so. Otherwise, when we post out and tell them to prepare for test. Tell your classmates to prepare for test. And the test is going to be on the three topics or three major areas that has been given to you by the three lecturers. So prepare yourself. In the next few days, we're going to inform you where. Pass the information to others. Yeah. Can you hear me now? Hello, can you hear me? My mic is the only one on. Why is it difficult for you to hear me? Can you hear me now? Can you hear me now? Yes. Okay, thank you. The information is this. Send information to the class reps. I have a WhatsApp platform that I've been using to communicate with the class reps. 3 lecturers have taught you, and I'm saying in the next few days, we are going to give you tests, and the test is going to be online. It's going to be part of the CA. It's going to be online, and so you must tell your class rep to put his or her name on my WhatsApp platform for class reps, because the test is going to be online, and so I'm going to send the link for the test through the WhatsApp platform very soon. I said we are going to tell you. That's why I need to make sure that you have your class rep on my WhatsApp platform. That is to answer your question. Please, sir, when will the test happen? You can't hear me. I don't think your phone is good, or the platform you are using is good. So tell others we are going to have tests very soon. I'm going to communicate the date to you. All I'm going to do now, ask the lecturers that I've taught you, the 3 of us that I've taught you, to put some questions together. And I'm going to send it to you via your class rep, the link that you're going to use in interacting with the questions that we're going to give you. Thank you for your time. See you on Monday. Another lecturer is going to come in on Monday. And Monday's lecture, next week's and upper week's lecture, are all about calculations, stoichiometry. So you cannot afford not to come or to watch the video of the lectures later. You cannot afford not to come. Some students have not been coming for lectures. We cannot help you if you don't come for lectures. Thank you. You must come on any Android phone. will be able to take the test. So prepare yourself. We cannot help it if you don't have an Android phone. Without the Android, it's very difficult to give tests to over 3,000 students. We don't have a place that can contain all of you. So the only thing we can do for now is to have an online test. Thank you for your time. See you on Monday. Bye.